Well, good afternoon and welcome everyone to today's webinar, Air-to-Water Heat Pumps, a Market Opportunity for Hydronic Professionals. My name is Doug Picklick. I'm the editor of HPAC Magazine, Canada's leading business publication for mechanical contractors and their supply partners. Today's webinar is generously being presented by Caleffi Hydronic Solutions, creating innovative, superior performance hydronic and plumbing products that help customers live comfortably and economically. The webinar today is part one of a two-part series on the topic of air-to-water heat pumps. Part two of this series will be taking place November 20th at 1 p.m. So please stay tuned and register for part two to get the whole story. Today's session should run about 50 minutes, and there will be time for questions and answers at the end. So please enter any questions you have into the question box on your screen, the GoToWebinar control panel, and we will try to get to all of them and still wrap up on time today. Also, the presentation itself, the PowerPoint, is available for download. It's on the Handouts tab on that same screen. You'll see it below. And this session is also being recorded, so it will be available for review after today. Before we begin, I'm proud to introduce our speaker, a hydronics industry leader and passionate teacher. John Siegenthaler is a licensed professional engineer with over 35 years experience in the understanding and proper application of water-based engineering principles and technologies. John is the founder of Appropriate Designs, a company that focuses on state-of-the-art applications of hydronic heating, and he's also the author of books including Heating with Renewable Energy, published in 2016, and Modern Hydronic Heating, now in its third edition. John is also a regular conference speaker and contributor to industry publications, including our very own HPAC Magazine and Modern Hydronics. Once again, it is my pleasure to introduce Mr. John Siegenthaler. Take it away, John.
Well, thanks, Doug. Great to be with you folks. I just want to start out by saying I do miss you. I've not been in Canada for quite a while, the border being closed and so forth. Hopefully I'll have an opportunity to come back up. Always have great experiences. We have good turnouts for training, and there's a lot of interest in hydronics up in Canada. So with that, let's talk about today's topics. We're going to start off, I always like to start off any session that is going to involve hydronics with fundamentals. Why do we choose to go to water-based delivery with a heat pump instead of, let's say, air-based delivery? What's the advantage there? And then we're going to get right into the fundamentals of what an air-to-water heat pump is for those of you that have never worked with these systems before. If you're familiar at all with basic refrigeration, basic heat pump operation, you'll see these are not that different from other types of heat pumps. They take, in the winter, they take heat from outside air by using a refrigeration circuit, and they put that heat into a stream of water, or it could be a mixture of water and antifreeze, and that's what goes in and heats the building. So we're configuring a heat pump to gather heat from outside air, as opposed to, let's say, from a geothermal earth loop or a pond or a lake. And we're also configuring that heat pump to interface with a modern hydronic distribution system. We'll take a look at the thermal performance of those heat pumps. What are the parameters that affect the heating capacity, the cooling capacity, and the efficiency of the heat pump? And then I really want to focus on why this is a market opportunity in North America. We'll take a look at what's happening globally with air-to-water heat pumps, and you'll see that, like many other past trends, technology that had its origin in many cases in the European hydronics market eventually migrates over to North America. And this, I feel, is going to be another example of that. We'll finish up with a very quick look at some what I call new concepts in air-to-water heat pumps. And then, as Doug was saying, part 2 will get into much more detail on system design, performance simulation. If you're designing systems around these, you definitely want to come back for part 2. So again, why do we want to combine hydronics and heat pumps? Why not use an air-to-air heat pump and call it a day? Well, we're going to start off with fundamentals here. What's the comparison between moving heat around with water versus moving it around with air? So on the air side, we use devices like this, a blower, and we push that air through devices like this, flex duct. I always like to say this is the third greatest invention of mankind. It comes right after duct tape and WD-40. Flexible ducts with really long zip ties, not really a pristine distribution system. If we go to water, we can use a much smaller and much lower power device, a circulator, a modern one with a ECM motor in it. And we can push that water through much smaller, what I'll refer to as conduits. You know, we call them pipes or tubes. You're looking there at 1/2-inch PEX aluminum PEX tubing that is being routed along floor joists, in some cases through the floor joists, much less invasive to the structure compared to a properly designed duct system. So why is this the case? Well, I won't bore you with a lot of chemistry, so to speak, but I want you to look at an index called heat capacity. It's how many BTUs a substance, 1 cubic foot of that substance requires to take its temperature up 1 degree Fahrenheit. And for water, a cubic foot of water needs 62.4 BTUs to raise its temperature by 1 degree Fahrenheit. Now, if we compare that to air, air only requires 18 thousandths of 1 BTU to raise a cubic foot 1 degree Fahrenheit. So we look at these physical properties of water versus air. These are nothing you can change. This is simply what we're given to work with. So when you make a comparison, I like to do a ratio. So if I take the heat capacity of water and divide it by the heat capacity of air, and round up, it's almost a factor of 3,500. So what does that mean? Means a given volume of water can absorb almost 3,500 times as much heat as the same volume of air for the same temperature change. So water is a thermally dense material. We can pack a lot of heat into water. So when that water goes through a pipe or a tube, it's carrying a lot of heat compared to a comparable volume of air, almost 3,500 times more. And that has huge implications. For example, here we're looking at 2 equivalent heat transport systems. The one on the left, a 3/4-inch tube, carrying water under normal hydronic design conditions like 4 feet per second flow velocities. And then the duct system, 14 inches wide, 8 inches tall, again, using standard procedures, standard numbers like 1,000 feet per minute for a trunk duct. So that 3/4-inch tube carrying water can convey heat at the same rate as a 14/8 duct carrying air. And obviously, I've shown this thing here, and I've shown it as if you could take a Sawzall and do what we call Sawzall surgery. We're going to cut up into that floor joist. That's a 2x12 floor deck. And, you know, I'm showing it as if you could cut that out. And of course you could, but in the process, you'd destroy the structure. So again, back to the advantage of hydronics, much less invasive, much smaller tubing, much easier to integrate both in new structures and into retrofit situations. Now, I also want to give you another very clear distinction between water and air. And to do that, I'm going to define something called distribution efficiency. And the folks that are tuned in today, I'm sure all of you hear this word efficiency probably every day you work. You probably hear it multiple times. Any efficiency is a desired output divided by a necessary input. It's always a ratio of output divided by input. So when we look at the distribution system, and for the time being, I want you to forget about the heat source or the cooling source. This has nothing to do with how the heat is produced. It's only about how it's moved through the building. So we're going to define distribution efficiency as a rate of heat delivery in BTUs per hour divided by the rate of energy use by the distribution equipment. That would be one or more circulators in a hydronic system, or typically a blower fan in a forced air system. So here's a quick example. Say we have a hydronic system. Under design load, it can deliver 120,000 BTUs per hour. And we've got 4 standard permanent split capacitor motor wet rotor circulators at 85 watts that have to run to deliver that 120,000 BTUs per hour. So really simple. You just take the rate of heat delivery and you divide it by the total watts that is necessary to make that heat delivery. And we get this number over here, 353 BTUs per hour per watt. You're probably looking at that and scratching your head saying, well, what does that mean? Well, it means for each single watt of electrical power to operate this particular distribution system, it's delivering 353 BTUs from where the heat was produced to where it's needed in the building. Okay. Now, the next question is that good? Is it bad? Or is it kind of middle of the road? But you don't have anything to compare it to. All right. So we got to come up with a comparison. So I'll take an example of and I'll say an older furnace with again, a permanent split capacitor type or shaded pole motor, not the most efficient motor technology compared to today ECMs. But let's say we've got a furnace that delivers 80,000 BTUs per hour, and that blower is requiring 850 watts to make that delivery. So again, we just do a ratio. 80,000 BTUs per hour divided by 850 watts, we're at 94 BTUs delivered from where it's created to where it's needed per watt. And you can see in this comparison, and these are just 2 specific systems here, the hydronic system is almost 4 times more efficient, or we could say the hydronic system is delivering comparable amount of heat, same amount of heat, using almost 1/4 of the power required by the forced air system. And it can actually get a lot better than that. I worked out some numbers on a system here using panel radiators in what's called a home run distribution system. That could deliver 30,000 BTUs per hour. And we worked out the flow rates and the heads that would be required here. And we worked that back into the efficiency of a small ECM circulator. And that could actually deliver 30,000 BTUs per hour using only 8.6 watts of electrical input power. Very, very small. And look at what the distribution efficiency is here. We're actually delivering, in our calculations, a little over 30,000 BTUs per hour. So we're over 3,500. All right, so let's make a comparison. Let's compare that furnace, 80,000 BTUs per hour, requiring 850 watts. So we had 94 BTUs per hour per watt, compared to what we just looked at. And again, look at the ratio of those 2 distribution efficiencies. What this is saying is that the hydronic system, this specific, well-designed, state-of-the-art hydronic system, is delivering heat using about 2.6% of the electrical input power compared to that older generation furnace system. This is a huge inherent advantage of hydronics, regardless of whether it's a heat pump providing that heat or a boiler or solar collectors. And it's an often undersold benefit, I'll call it. Oftentimes we find that contractors or those that are marketing hydronic systems, oftentimes they get hung up on things like AFUE, the efficiency of the boiler, the COP of the heat pump, and they don't educate a prospective customer about the inherent advantage of delivering heat with water versus air in terms of overall electrical energy use over the life of the system. This can mean thousands of dollars in cost savings. So it's there, it's real, the physics prove it. It's something that if you talk to homeowners, especially those that are focused in on energy efficiency, it's really something you want to talk about. So that's the kind of the prelude into why hydronics. Now, let's get right into fundamentals of air-to-water heat pumps. Most heat pumps today are reversible, meaning they can act as a heating machine or as a cooling machine. And that is the case with air-to-water. So what we have in heating mode operation, wintertime operation, we have basically a 4 standard function refrigeration system. We have an evaporator, a compressor, a condenser, and a thermal expansion valve. They are specifically configured in this case so that in the winter, we're absorbing heat. Our evaporator portion of the refrigeration system is taking cold outside air, and it might be air literally at 0 degrees Fahrenheit or even colder. And we're extracting heat from that. And, you know, some people wonder, how do you get heat out of 0 degree Fahrenheit air? Well, if you take 0 degree Fahrenheit air and cool it to -15 Fahrenheit, you've extracted heat from it. Now, granted, that's very low-grade heat from the standpoint of using it for a practical application, but that's the beauty of a heat pump. What a heat pump does is essentially takes low-grade heat and pumps it to higher-grade heat, higher temperatures that we can use. And that's what's going on with the refrigeration system. I won't take the time to walk you through all the details, but basically it's the same thing that would happen in any other heat pump. Now, one of the components that you see here is a reversing valve. And all that does is it basically flips the function of the evaporator into condenser. In the cooling mode, that air coil is dumping heat to the outside air. We're dissipating heat. And the hydronic side of the heat pump is where the chilled water is being created, circulated back into the building. So basically, in winter, we produce a stream of warm water with the heat pump. In the summer, we produce a stream of chilled water. Okay, there's a couple common configurations for air-to-water heat pumps. I refer to one of them as a self-contained. The common term, and I believe this term came out of Europe, it's called a monoblock, and it actually is spelled that way without the K. Monoblock, when you hear that term, what that means, the heat pump is self-contained. All the components of the refrigeration system, the controls, everything is in that box, and it's factory charged with refrigerant. To install it, you need to physically place it on a base. You need to connect 2 pipes and the electrical to it, but you don't need to get out tanks of refrigerant and start charging it. That refrigerant's already there. In a warm climate, in Southern Europe, for example, in Italy, they will just run the water directly outside. Now, in Canada, that's not going to be a good idea. It would be fine if the long as the heat pump is operating, but if you had a power failure during sub-freezing weather, or if the heat pump has some kind of a service issue and it's very cold out, obviously that water is going to freeze and cause some damage. So most of the systems that we're going to get into in part 2, most of them will use antifreeze if it's a monoblock heat pump. And you can either run the entire hydronic system on antifreeze, or you could put in a generously sized heat exchanger and just run a short circuit between that heat exchanger and the heat pump, and then have water on the other side. Making that decision, really, it depends on cost. You will get a performance penalty when you put a heat exchanger in, because you have to have a temperature difference to drive heat from the heat pump side to the system side. How much of a temperature difference depends on how large that heat exchanger is. But one of the cardinal rules, and again, we'll talk about it more today and emphasize it part 2, you want to keep that heat pump running at the lowest water temperature or the lowest fluid temperature possible. That's where you're going to get the best efficiency. So anything you can do on a system side to bring that water temperature down is going to be to your advantage. So honestly, I've done systems both ways. I prefer to use antifreeze through the entire system today if it is a monoblock heat pump that we're working with, rather than put the heat exchanger in. The other aspect of the heat exchanger, you're going to need 2 circulators. So you'll have a higher installed cost. You also have a higher operating cost. Now, another common configuration, well, here's, before I get to that, just some examples of monoblock heat pumps that are on the North American market now. AirMech is distributed out of Canada, Arctic, a couple Space Pack units down here, Chiltrix, Asian-built product, but it's distributed in the U.S. out of Virginia. And there are others. I'm just throwing these in as examples so you can see kind of a commonality there depending on the capacity of the heat pumps. The ones that have the 2 fans are probably up in the 4 to 5 ton range. That one with a single might be about a 3 ton or maybe a little less than 3 tons. So basically it's a box. It has fans, it has a coil, it has a compressor. It may have a display on the outside. It has connections in some cases in the rear, some cases on the side. Okay, now the other common configuration is what's called a split system. Now we have an outdoor unit and an indoor unit, and we're connecting them with refrigeration piping, refrigeration line sets. Residential 4 or 5 ton unit, usually it'll be like a 5/8 or 3/4 inch suction line, and then the liquid line is going to be a 3/8 line. So what are the advantages and disadvantages? Well, one big advantage is there's no water outside, so you don't have to worry about antifreeze. Nothing can be damaged by freezing outside. That is a significant advantage. Another, well, I guess I'd say a potential disadvantage is these need to be serviced in the field with refrigeration equipment. When you put the line set in, you need to evacuate it with a vacuum pump, and then you open service valves. There is enough refrigerant in the outdoor unit to cover so many feet of line set, typically 25, maybe 30 feet of line set. If you're going farther than that, you're going to have a way to add. Most of these are R410A refrigerant. So you do need to have experience with basic refrigeration skills, vacuum pump, putting on a set of service gauges, adding refrigerant if necessary, and so forth. So we could say the monoblock is simple from the standpoint, if I only want to deal with water or water-based antifreeze solutions, a monoblock doesn't require me to deal with the refrigeration, at least initially. Now, down the road, if you do have to do service, maybe 10, 15 years out, you may have to have somebody come in and do some work on the refrigeration system. So that's the basic difference between a split system and a monoblock, and there are products in both of these categories on the market today. Here's an example one. This is actually a Canadian product, comes out of Maritime Geothermal. This one is a split system. You can see down below, here's the outdoor unit. That outdoor unit in this particular product, Nordic, only has the outdoor coil and the fan. The compressor is actually inside. And I like that for a couple of reasons. One is it brings most of the electronics and the electrical components inside the building. So they're going to have less exposure to the elements, obviously inside a building versus outside through a Canadian winter. The other thing that does represent an option with this particular configuration is you can order this with a domestic water desuperheater, which means you can do at least some domestic water preheating with this unit, because again, none of the water has to go outside. So that's an example of a split system. All right, let's talk about thermal performance. All right, basic operation of any refrigeration circuit. We're going to absorb low-grade heat at our evaporator. That causes the refrigerant to evaporate to a vapor. It's going into a compressor. Compressor is going to bring up pressure and temperature. We're going to send the hot refrigerant gas through the condenser. It's going to transfer its heat off. In the case of air to water, it's going to transfer it to water stream. And then finally, that refrigerant is going to go back through an expansion device, and that returns it to the same condition where it's ready to make another pass through the evaporator. So whenever that compressor's on, this circuit is operating continuously. And the measure that's used to gauge the efficiency is called coefficient of performance, or COP, and it's simply the ratio of how much energy is being delivered to the load divided by the rate of energy input to operate the heat pump, the vast majority of which goes into the compressor. So if we know the electrical input here in watts, we convert that to BTUs per hour, so we have the same units in the numerator, denominator. That's what a COP is. Now, I want to stress to you, a COP is an instantaneous performance index. if any of the operating conditions change, such as the outdoor temperature or the water temperature leaving the heat pump, that is going to change the COP. So don't say that you have a heat pump with a COP of 3 or 4 or whatever the number is. That's a snapshot. That COP is going to vary considerably, even over an hour's worth of operating time, depending on, again, changes in outdoor temperature or water temperature. We could define other COPs. One that I will talk about in part 2 is called a seasonal average COP. That's sort of like the equivalent of an AFUE rating on a boiler. But to get that, you really have to mix a lot of information together. What are the ranges of outdoor temperature? What are the ranges of water temperature the heat pump's working with, and so forth. And again, that'll be in part 2. Now, the easiest way to remember what affects heating performance is to look at what I call temperature lift. In this case, it's the change in temperature between the outdoor temperature and the water temperature that's leaving the heat pump going off to your load. We call that the temperature lift. Remember, there's a lot of heat in outside air, even at low temperatures, but we have to lift the temperature of that heat to a value that we can then use to heat the building. Anything that brings these two temperatures closer together, in other words, anything that reduces the temperature lift, is beneficial. It's going to give you higher heating capacity and higher coefficient of performance, and vice versa. Anything that pushes them farther apart is going to lower the performance of the heat pump. Now, if you look at manufacturer's data, here's an example. What we're plotting here is outdoor temperature over a pretty wide range and heating capacity, BTUs per hour output of a particular heat pump. And you'll see 3 curves here, and these are for 3 different what are called leaving water temperatures. This is the water temperature leaving the heat pump's condenser. And you can see the higher that temperature is, the lower the heating capacity for any given outdoor condition. So if it's 40 degrees Fahrenheit outside and we're trying to produce 131 degree leaving water, we have a certain capacity here, maybe 37,000 BTUs per hour. But if we were to only require 95 degree water, we're substantially higher. We're up maybe 47,000 BTUs per hour. Percentage-wise, that's a big increase. So what is this telling you? It tells you that low water temperature distributions are really important to get the best efficiency out of air-to-water heat pumps. It's the same story with geothermal water-to-water heat pumps. It's the same story really with any heat pump, because anything you can control that can bring those temperatures closer together between the source temperature and the load temperature, the better the performance. The coefficient of performance, similar relationship here. The higher the water temperature, the lower the COP, and the lower the outdoor temperature, the lower the COP. And you can see an extreme condition here. It's 10 degrees below 0 Fahrenheit outside. We're trying to do 130 degree water. We're actually at about what? About 1.8 on our COP. If it was 40 degrees out, we'd be up around maybe about 2.7. Pretty significant increase. Okay. So again, think about temperature lift. You can't control outdoor temperature, obviously, but you can control to some degree the water temperature that's necessary in that hydronic distribution system. Okay. I just want to mention real quick what are called EVI, or enhanced vapor injection systems. Really quickly, what an EVI system does is it lowers the temperature of the liquid refrigerant coming out of the condenser. It lowers it farther than a standard refrigeration system can. And you might say, well, so what? What does that do? Well, it means you can absorb heat from even lower temperature outdoor air. There actually are some air-to-water heat pumps on the North American market now that can operate as low as minus 22 degrees Fahrenheit. So extreme cold conditions. Now, I'm not going to tell you you're going to get a COP of 3 or 4 under those conditions. You're not. You're probably going to see COPs in a range of maybe 1.2, 1.4. But remember, those conditions are extreme. They don't last very long in most areas, especially southern areas in Canada. Yeah, Yellowknife, probably if you see several days every winter. But the takeaway here is air source heat pumps have evolved a lot in the last couple of decades to the point where they can operate in sub-degree Fahrenheit climates. That was not the case back in the 80s and the 90s. Air source heat pumps pretty much just suitable for more temperate climates. In the United States, southern states maybe up around, Missouri, Maryland, that area. Upstate New York, where I live, we're at almost 8,000 degree days in a typical winter. Not, air source heat pumps 3 decades ago, pretty much forget it. That just not going to work here. That actually is what gave rise to the geothermal industry. Okay, cooling performance, real quick. The colder the water you're trying to produce, the less efficient the heat pump and the lower its capacity. You have a set of curves like this. And again, if you download the PDF, if I go a little fast through here, you can look at these curves in more detail. But what you're going to see, again, the lower the chill water temperature, the lower the performance of the heat pump, and vice versa. So again, if you can design a chill water cooling system and work with maybe 50 to 60 degree water versus 40 to 45 degree water, you're going to see a benefit in terms of better cooling capacity and better efficiency. So let's switch now from kind of the technical side. Why is the market going to grow? Okay, I just want to show you some global statistics. Now this goes back just a couple months ago. There's a publication in Japan called JARN, and they put out statistics on a lot of different market sectors. And air-to-water heat pumps is one of the global markets they follow. Last year, 2019, over a 25% increase in the market globally, and it reached a demand of about 3.4 million units. So even though this technology is relatively new, and quite honestly, a lot of HVAC people in North America probably have never heard of an air-to-water heat pump at this point. That's not the case globally. The big markets are China and Europe, 2 strong hydronic markets. In Europe, about 600,000 units last year. France is a big heat pump market because they're very electrified. Germany, Italy, 2 very strong hydronic markets, and other countries as well. And a lot of this was pushed by plans to phase out fossil fuels. There are incentives in European countries similar to the incentives we have here in the States, not on air to water at this point, but there are very strong incentives on geothermal heat pumps, and I'm sure there are some heat pump incentives available up in Canada at this point. So what are some of these Asian manufacturers, air to water heat pumps? I'm sure you recognize most of those names on that list: Daikin, Mitsubishi, Fujitsu. These are all companies that sell ductless mini split heat pumps in North America. They have air to water heat pumps. If you look at their global websites, they just have at this point chosen not to bring them into this market yet. That is changing. That is changing. I'm going to tell you within the next couple of years, you're going to see 2 major entries into the North American market. And I won't go any farther than that other than tell you they finally have looked at this market, said maybe it's time we have some product here. German manufacturers, I'm sure you'll recognize Viessmann, Bosch, Vaillant, Wolf, Dimplex. These are all other fairly large manufacturers that offer air-to-water heat pumps. And then, as I mentioned, several in Canada: Thermatlantic, Nordic, Arctic, and Airmet. So globally, this is a strong market. And to show you that, Germany, this is probably one of the strongest hydronics markets in the world, always has been. It's certainly it's the home to the 3 largest boiler manufacturers in the world. But in 2017, the sale of heat pumps for residential heating in Germany exceeded boiler sales. That was in 2017. And here's the graph that shows it. Okay, so if I start here, basically the black bar here represents boiler sales as a percentage of new homes based on their building permit requirements. They have to specify what's being used. And the green bars represent heat pumps. And it's slow here, but you can see that boiler sales are slowly declining as a percent of new residential heating installations, and air-to-water heat pumps are actually, well, I should say heat pumps in general, but remember, this is a very strong hydronics market, so a lot of these are going to be air-to-water heat pumps. Some will be geothermal as well, but there's definitely a trend towards electrification and heat pump technology in these strong hydronic markets, okay? Now, what about North America? What are things that are going to push it? Well, net zero houses. This is a very strong, or I should say a very rapidly growing market, especially in Canada. I don't remember the exact number, but I do remember, I believe it was a couple of years ago, the growth in net zero buildings was something like 200+% in the Canadian market. So a lot of builders and a lot of consumers are opting to go this route towards net zero, where the energy used in the house over the course of the year is basically produced on site. And the only practical way to do that is with electricity, and in this case, photovoltaics. So electric houses, all electric houses are becoming much, much more prevalent in this market. And obviously, a low energy use house where you want to use electricity begs for a heat pump. So heat pumps are being used. Many of them are air-to-air heat pumps or ductless mini splits at this point, but don't give up on that hydronic niche because net zero houses can use hydronic systems. Now, in the US, I'll give you some interesting things here. The US market right now does have a 26% federal tax credit on geothermal installations. That was 30% last year. It's going down to 22% next year. And assuming that legislation doesn't get modified, it's going away at the end of 2022. 2021. At the end of 2021, it goes away. Now, an interesting thing that happened back in, I believe it was 2017, at the end of 2016, this tax credits, they were in place for 8 years, they expired. So into 2017, there were no tax credits, and the market for geothermal went down by 50%. And what happened next, typical Washington politics, there was a massive spending bill passed back in February 2018, and they were reinstated, okay? But here's the deal. Do you want to base your business model on rebates? Yeah, they're great when they're there, but if you build a strong business model and you're counting on these rebates and the politics change and the rebates go away, that really changes the economics a lot, okay? Another thing, air-to-water heat pumps are significantly less expensive to install compared to geothermal. Obviously, you're not installing the earth loop, and that is probably, in some cases, at least half the cost of the overall installation. So if a geothermal system costs X dollars, you can do an air-to-water heat pump, our estimates, anywhere from about 30 to 50%. Much, much less expensive. And again, right now, we do not have any subsidies on air-to-water heat pumps in the States, with the exception of Vermont. They do have a program in Vermont. But for the most part, these are unsubsidized, going against a heavily subsidized geothermal market. The return on investment still looks favorable for air-to-water because of this reduced cost, okay? And obviously, the cost of geo varies a lot with how the loop's going to be installed. Is it going to be boreholes? Is it going to be a trench? Do you have the land area to do trenches? In my area, vertical systems run about $3,000 per ton just to put the borehole and the pipe in. So that, easily $12,000, $15,000 just to put the earth loop in. And, that's obviously a cost you don't have with the air-to-water. Another thing, geo, I guess it's somewhat obvious, but geo is very disruptive to the landscape. Now, if it's new construction, you got a lot of area, you've got a big track hoe available, sure, you can dig up trenches and bury pipe, and we've done this, okay? If it's existing finished landscape like this photo down here, yeah, you can dig it up, you can put the pipe in, put the dirt back in, remember, a part of that cost should be restoring that landscape back to its original condition. So as an HVAC contractor, do you want to be out there raking up the rocks, putting the grass seed down, doing all the restoration work that you might have to do just to put that back in its original shape? And those costs really should be included as part of the overall system, even if those are going to be subbed out. So another thing, domestic water heating. You can't really do that. Well, I shouldn't say you can do that with certain geosystems with these superheaters, but you really can't do that with a ductless mini split. And what's happening as house heating loads are getting smaller, the domestic water load can be anywhere from 25 to 30%. And real quickly, I've done the math on this. Family of 4, 60 gallons per day of domestic water heated from 50 to 120 degrees Fahrenheit. If you do it with an electric water heater versus doing it with a heat pump and assuming a seasonal average heating coefficient of performance of 2.5, you're actually saving about $270 a year just in domestic water heating compared to doing it with electric resistance heat. So it's not always just about space heating or cooling. That domestic water load is significant. Another thing, I'll just turn all this on. Again, I'm going to encourage you to get the PDF and read this through in detail. But oftentimes the COPs that you see in literature for geothermal heat pumps do not include the power to operate the earth loop circulators. Or if they do, there's a certain ANSI standard that's mentioned here. I've looked at that ANSI standard in detail. There is a calculating procedure to get an estimate of that power. In my opinion, it's not accurate. They're only looking at the pressure drop through the heat pump, not the pressure drop through the earth loop. And obviously you've got to pump through both. So if we, and I ran some numbers, if we put in a heat pump here with a little over 2 tons of capacity, and we do our math on the earth loop, and we include the power to operate the earth loop circulator in the COP of what I'll call the heat pump plus the earth loop circulator, because you can't operate a geo heat pump without an earth loop circulator. It takes that COP from perhaps a published value for the heat pump only, 3.4, down to about almost 3.0. So as we throw more and more pumping power at a geothermal earth loop, we're actually taking away from the true system COP. All right. And again, if you're doing geo, it's not my purpose to just shoot a bunch of holes in the geo market by any means. But realistically and from an engineering standpoint, you should be including the cost to operate the earth loop circulator as well as the heat pump itself, because that is what your customer is going to pay for. And by the way, you don't pay for COP. I challenge you to look at your electric utility bill and find a line item that says COP if you have a heat pump in your house. You pay for kilowatt hours. And again, there's some calculations here, but I'll summarize it quickly. The higher the COP, the lower the heating cost is going to be, okay? However, as building loads get progressively smaller, building codes are forcing heating loads getting smaller and smaller. The difference between the heating cost with a high COP heat pump versus a lower COP is in some cases not a lot. And I did a quick example here, a house in Syracuse, New York, 6,700 degree day climate. I compared a geo with a seasonal heating COP of 3.28 to an air to water with a seasonal COP of 2.8. And it works out to be about, let's see, right around $100 a year, okay? So let's say a hypothetical, let's say it was an extra $10,000 to install that earth loop. You got back some of that, so let's say your net cost was $7,000 to install that earth loop. How are we going to amortize that extra $7,000 with a savings of $99 a year? You can't. The heat pump will be out of service by the time you're even approaching any kind of a payback on that. So keep that in mind. It's not always about who has the higher COP. It's about the overall kilowatt hours that a given system is going to require, and then total owning and operating cost. Okay. Finally, I'll finish it up. I put down here, boilers don't offer cooling. This has been a game changer, or I'll say this has been a lead loser for a lot of years. Somebody gets excited about using hydronic heating, and then they ask the question to the contractor, what do I do about cooling? Well, if you want cooling, you may have to go to a completely separate system and maybe use a different subcontractor to put that in. Okay, that's really not what they're wanting to hear. A lot of people today want cooling. A boiler can't do it, a heat pump can. So chill water cooling is something we've talked about in several past HPAC articles. There's several different ways to do it. Right now, I don't want to get into those in detail, but basically you're producing chilled water with the heat pump, and you're going to route that chilled water through some type of distribution system. It might be zoned, or it might be a single zone. You know, you could do multi-zone heating and single zone cooling, or almost any combination there. But this gives you the ability to offer your customers cooling, which you can't do that with a boiler. Right? So ductless mini splits, they're very popular today. I'm sure they're gaining good market share up in Canada. They work, they're plug and play, they're pretty easy to put in. I put down here what one of the green building websites down here in the States puts out for suggestions. And essentially, I'll summarize. Put a couple of these in, maybe 3, put one in the hall, put one in the living room, and just keep the doors open so the air will flow through the building. That, in my opinion, is not a well-designed distribution system. Yeah, if you have a really good thermal envelope, you won't have a lot of temperature differentials, but they actually suggest here, you know, if you keep the bedroom doors closed at night, the room cools down, you may want to put an electric space heater in there. Come on, this is a compromise in comfort. Some people will do this for the sake of keeping the kilowatt hours down. In general, this is a compromise, okay? So one of the things you'll see with this kind of heat pump, several manufacturers will talk about the fact they can maintain capacity at sub-zero Fahrenheit temperatures. Ask them about COPs at -10 or -15 or -20 degrees Fahrenheit. Those COPs are not good, okay? So there was some field testing done a few years ago in Vermont. This just shows some scatters. What's the daily COP of some of these mini splits? You know, they're not 3 and 4. They're in that range, maybe 1, 2 in some cases. Cold climates, air source. Yeah, the low ambient heat pump designs with the EVI refrigeration systems, they can work pretty good at sub-0 degrees Fahrenheit, but they're not producing COPs up in that 3 or 4 range. Think about what I think is a good performance. If you're producing 120 degree water when it's 0 degrees Fahrenheit outside with a COP of 2, you've got a good heat pump. Okay. Again, comfort. Okay. Ductless mini splits. Any air source heat pump has to have a defrost in a cold climate. With a ductless mini split, you're pulling heat, literally, you're pulling heat out of the room where those cassette units are mounted to melt the frost in the outdoor unit. You're blowing cold air into the room to do that. With an air water system, that heat's coming out of a buffer tank. It might be coming out of a slab in a floor heating system. You'll never feel it. The energy has to go out there. You have to melt the frost, but it's a matter of how do I conceal that energy? Not trying to hide it. It's simply you're not trying to create discomfort by defrosting the outdoor coil on that unit. Okay, so again, air to water, you're not going to feel it. So again, ductless mini splits, they provide heating and cooling. If you go to air to water, look at all the things you can do here. Room by room zoning is easy. Radiant convective heat delivery, if you're doing radiant panels, floors, walls, ceilings, panel radiators. You could do zoned cooling if you want to. You can do domestic water. Some heat pumps can have a secondary heat exchanger that in the summer, if you happen to have a pool, instead of dumping heat outside to cool the house, you could dump it into a swimming pool, okay? You have the advantage of much higher distribution efficiency on moving that energy around through the building. And you don't have, at least in the case of a monoblock, you really have no refrigerant inside the building. With a split system, you do have a small amount of refrigerant inside the system as a whole, but compared to a large VRF system, much, much less refrigerant in the system. So a lot of advantages there, okay? Real quick, new concepts for air-to-water heat pumps, just to give you some ideas. This is a Canadian company, Thermatlantic. You can just put that name into Google, and I'm sure you'll go to their website. What Thermatlantic is doing is building this box here, and I call this the hub of the system. Essentially, what they've done is they've recognized that they can't sell condensers and be directly competitive with the big guys like Lennox and Trane and York. So it's bring your own condenser and hook it up to our hub, and also hook up a buffer tank, perhaps an electric boiler for supplemental heat, and build a system around that. And again, on the PDF you can download, you can look at this, or you can look at it on their site. They're essentially building the components to put together the condenser, the buffer tank, a chill water air handler, and some type of a low temperature hydronic distribution system for heating. And they're organizing the physical hardware and also the controls into this product. It's a really interesting concept, innovative concept. I don't know of other companies that are doing this, and check them out. One of my favorite variations on air to water is an interior air to water. To my knowledge, there are none offered in North America at this point, hopefully in the future. What are we doing? We're simply ducting outside air through an air handling section in this heat pump, and we have our hydronic section in the same heat pump. So it is, from a functional standpoint, a monoblock, but it sits inside, and you can see the large, in this case, flex duct that goes to an outside grill, brings air in, goes through the air handler, pulls the heat out of it, pushes the air back outside. The nice thing about this is it's not outside. Your controls, your electronics, everything's inside. It should have a life comparable to a geo heat pump because of that. It doesn't force, microelectronic components to be in an outdoor unit. You don't have to use antifreeze with it. Which would you rather service, that unit in a basement or standing in a snowbank in January and, trying to deal with the outside unit? So I do see advantages, benefits of these. There are several companies in Europe that offer these. They just haven't migrated to the North American market yet. Here's an example. This, I believe, is a Dimplex unit out of Germany. I want to show this. The air handling section is just the coil and the fan up here at the top. Here's your refrigeration system with a built-in buffer tank, compressor, expansion tank. And what they're doing is they're actually setting this up in the corner of a building. So they have very short ducting, probably on the order of maybe 1.5 feet of ducting, bringing air actually in here, running it through the air handling section, pushing it right back outside. The way they've set this up, you can configure that upper air handling section so you can go around a corner like this, or you can go straight through it. So I really would encourage this kind of a heat pump to be available in the U.S. It's not going to work everywhere. It would work nice in slab on grade buildings where your exterior walls are all above grade. Your mechanical rooms are typically above grade. If it's below grade, that presents a difficulty in terms of trying to get that outside air. You'd have to go up and out. So again, it's something I want to show you just as concept of how the generic model of an air-to-water heat pump can be applied. Okay. Now I'm going to wrap up here, and we should have just a couple minutes for questions. There's a lot more information available to you free. Caleffi produces a publication called Hydronics. Hydronics number 27 just came out in July. It's on the subject of air-to-water heat pumps. You can go to this website and download the PDF. When you're there, register, and they will ship you hard copies every 6 months. Hydronics has been coming out every 6 months now for roughly the last 13 years. A lot of detailed information on air-to-water heat pumps in there. Also, this is brand new with Caleffi. They now offer hydronics in a digital version, and this is nice. You can do a lot of things that a print version, or in some cases a PDF file, doesn't let you do. You can very quickly cross-reference. You can search for keywords. So from this point forward, hydronics will be the PDF file. It'll also be in print for those that have registered to receive it, and it will be in this digital format. And 2 days from now, Cody Mack, who's one of the tech service and training people at Caleffi, he's doing a what's called a Coffee with Caleffi. This is a monthly webinar series from Caleffi, 10 things to avoid when designing a hydronic system. This is a guy that's turned to wrenches for several years. He's got a lot of experience. These are all free. Just go to Caleffi North America and register for that, and I'd encourage you to take advantage of that. Finally, part 2 is coming up on November 20th at 1 p.m. Go to hpacmag.com, and it's not there yet, but very near future, there'll be a registration link for part 2. Again, we're going to focus on system design and performance simulation, pulling some of the hardware we've looked at today into overall systems, and look forward to having you return for that. And with that, Doug, I'm looking at my watch. I've got about 3 or 4 minutes. Do we have questions?
Okay, yep, there are a few questions came in. Brett asks, what is the largest size of the air-to-water heat pumps you've seen?
Well, with single phase units that are running on 240 AC, the cap is somewhere in the 5 to 6 ton range. Now, that being said, if you've got a 20-ton project and you don't have 3-phase power available, you can do multiple air-to-water heat pumps. I've seen systems with literally 7. That's kind of an exception, but 2 or 3 heat pumps, just like you stage boilers, you can stage these heat pumps. If you do have 3-phase power available, you can get, I know AirMech does 10-ton. I think they may even have some 20-ton units. So it really comes down to, is 3-phase power, is it a commercial building with 3-phase power? Then you can get these larger compressors get up into the 10, 20-ton range in a single machine. If it's typical residential single-phase 240, I'll say 5 to 6 tons is about as big as they can get in a single box.
Okay. Richard asked, this was when you were mentioning how heat pumps are outselling boilers in Germany. He asked, are the Germans using air-to-water heat pumps for residential cooling?
That's a good question. I don't know, but I suspect yes. And I say that, keep in mind that a lot of Europeans don't do cooling. And that trend, though, is changing, and I think the availability of heat pumps will probably alter that market. But if you were in Europe 20 years ago, in the summer, you probably just learned to open the windows and maybe turn on a fan. But I suspect the answer to that is yes. And I say that because there are products to support that. Chilled water fan coil units. There are several European manufacturers that offer, for example, console fan coils that do have drip pans in them, and that does allow you to do chilled water cooling. So I suspect the real drive is on the heating side, but that if the client does want cooling, there is the ability to do it.
Okay, this question is, what temperature can be achieved for domestic hot water with superheater?
A practical one is up around, I'll say 130. Heat pumps with these superheaters, some of them today actually have a high temperature limit on domestic water. They'll actually shut off the desuperheater circulator that's moving domestic water from the tank through that desuperheater coil if that domestic water heat reaches 130. The best performance is going to be where you set up a dedicated preheat tank and let that desuperheater work with the lower end of the domestic water heating range. So, working with water from maybe 45 degrees Fahrenheit up to 100, you're definitely going to get good performance from a desuperheater. If the unit continues to run, yes, we can get that water temperature up potentially to the point where it doesn't need to have any other temperature boost. So if you're going into a preheat tank with a domestic, with a desuperheater coil, usually what you'll see is some other kind of an electric resistance heater, either another tank or perhaps a tankless electric heater, to ensure that the delivery temperature is where it needs to be. Some codes may require 140 degrees with a tempering valve. From a Legionella standpoint, you're not going to get 140 out of a desuperheater with present technology.
Okay. I think our time is just about up. We do have more questions, so I'll let you know that for any question that hasn't been answered, it will not go unanswered. We'll collect the questions, John will answer them, and we will distribute the responses to everyone. Just a couple of comments. Tobias from Germany says, yes, I'm from Germany. Yes, I believe that means they do use it for cooling.
Okay.
AirMech, according to Jacob, does have up to 200-ton air-to-water heat pumps. And the COP nowadays on a geothermal heat pump is 6, according to Doug. So that's something
Well,
you have to consider.
yes, we can create lab conditions that'll give you a COP of 6. We could
Okay.
probably do that with an air to water. Don't count on a COP of 6 for a seasonal COP in a cold winter heating climate. It's not going to happen. Anyway,
Okay.
I do appreciate the feedback there from the industry. And I guess we got to close it out. Folks, come back on November 20th, register at hpacmag.com, and we'll see you then.
Yep, thank you very much. And early notice, HPAC Magazine will be holding our Modern Hydronics Summit virtually in March 2021, so please stay tuned for that. Thanks again, everyone who has attended, and large thank you to Caleffi Hydronic Systems for being our presenting sponsor of this series. For more information on Caleffi, visit caleffi.com. Thanks to everyone who's attended. We'll see you again in November. Until then, have a great day and stay safe.
Thanks, Doug.